Today we'll be looking at 2.5. It's the graph of y equals kx squared. So 2.4 was just looking at when we had kx, not the squared there. And we saw those were just linear lines or very straight lines, like diagonals, either sloping up or down. So today we're going to look at this, what happens when you put a 2 there and make it x squared. But still, direct variation. It's still y equals kx to the n, but now we're just talking about there being a 2 there. So how do I graph and identify important features of the equation y equals kx squared? And a lot of the stuff that we'll be looking at on the graphs will be using two different websites. But first, if you remember from 2.4, we did a lot of work with finding the slope of the line and then using it to find that's basically your k value. In this case, it's going to be a little bit different when we have a kx squared. So let's do our example here. The graph below shows the braking distance of a car at various speeds. It is defined by the function d equals 1 over 20 s squared. Find the following rates of change. We should know what that means. Rates of change is finding slope. And explain what each means in terms of braking distance. Okay. So we're going to find R1. That's the rate of change from 2020 to 4080. So if you look at that, that should be on this graph here. Let's use a different color so I can see it. 2020 is about here. See it right there. And then 4080 is close to there. As you can see, this goes by 25s up here, and this goes by 10s. So we're going to find the rate of change between these 2 points. If you remember, that was us labeling these x1, y1, x2, y2, and then doing the slope. So we're going to find R1, which they call that the first rate of change. So it's going to label R1. So we find the slope, which is doing your y2 minus y1. So that's 80 minus 20 all over your x2 minus x1, which is 40 minus 20 as well. So we'll get 60 over 20. And that's the same thing as 3 over 1. 60 divided by 20. So their slope is 3. All right, find R2. Now we're going from just 2 different points. We're doing 40, 80, which is one of the points that we used before. But now we're going to go to 60 to 180. So let's just highlight that here. So I'm still doing 40, 80, but then my next one's going to be 60, 180. So that's up here. As you can see, these 2 points, the distance between these 2 points is a lot steeper as opposed to the first 2. So would you think we'd get the same rate of change, or would it be different? So let's find out. Label these again. x1, y1, x2, y2. And then we have 180 minus 80. That's your y2 minus y1. And then 60 minus 40. So the top now is 100. The bottom is 20. 100 divided by 20, that is not the same thing as 3 over 1. That actually goes into it 5 times. So it's 5 over 1, or 5. Is the rate of change constant for this graph? Well, what do we basically find out? We have this graph, this arc that's going up like this. This is describing this equation. And we found 2 sets of points and found the rate of change. So we found it to be 3, we found it to be 5. So what's happening here is the rate of change, or the slope, in this particular case when we're trying to find slope, it's changing every time, which is different than when we did y equals kx. That had the same slope. No matter what 2 points you picked, it would always be the same slope. So is the rate of change constant for this graph? No. It actually changes. And it changes depending on what points you pick. So it's very different than having the y equals kx. So hopefully that makes some sort of sense. And also, what are we even talking about here? It's your speed and then your braking distance. So your y value is your braking distance. So it's really, we're finding your feet, your distance per 1 mile per hour. So this would be like it would take 3 feet per 1 mile per hour to stop. It's your braking distance. So 3 feet per 1 mile per hour. In this case, when you get to higher speeds, of course, when you're 80 or 180 miles per hour, it would take 5 feet for each mile per hour to slow down. So in this particular case, the rate of change is not constant for all equations of this form, y equals kx squared. I mean, we just talked about that. It's not the same. So we're going to do it again, but this time we're going to do it in the calculator. And in this case, we'll do it in the online calculator. Consider the equation y equals 6x squared. So we still have the x squared there. We're going to bring up a table in the calculator and pick 2 points and then find the slope using the 2 points. So I'm just going to do this, obviously not in the calculator, but in the Desmos calculator. We're going to type in y equals 6x, and then to put the squared, you have to put the arrow, shift 6 is what I press, and then 2. So you should be able to see it. And we're going to bring up a table. All right. Pick 2 points. So if you want more points, you can just click down here and then hit enter a few times. I don't think we need that many points though. So the idea is just to pick 2 points and find the slope. So what I would say is for you at home watching, you pick 2 different points than what I pick. So I'm going to pick, I'll pick 496 and 5150. You pick something different, do the slope, and we'll see that it should be different. Different answers. So 496. And you pick different ones. And 5150. So find the slope. In my particular case, if I was doing this, this would be 150 minus 96 all over 5 minus 4. So the bottom would be 1, and the top would be 54. So if you were to pick any other 2 points, you would hopefully see that we would not get the exact same answer. You pick your own 2 points, and it should be different. So again, the whole point, again, is not to have a constant slope. So there's no point in finding the slope because it's not the same. It's different every time with these kind of equations. So we kind of looked at one graph. You can kind of see the shape of it for this y equals 6x squared, if you see this here. But, what is this called? Have you maybe seen this shape before? Maybe you have, maybe you haven't. Kind of looks like a U shape. The graph of this, no matter what you put in for k, is called a parabola. Parabola. This vertical line that's a dotted line, it's coming down right here down the middle. This line that you can draw right down the middle, it kind of cuts the graph in half. You can kind of see it looks the same on both sides, right? Just kind of like a mirror image there. This is called the axis of symmetry. Symmetry. There we go. And if you ever heard the word symmetry, symmetry just means it's kind of the same on both sides. Symmetric means same on both sides. So in this case, when you draw this diagonal, this vertical line, it looks the same on both sides of the graph. And this very bottom point here, this arrow is pointing at the very bottom that goes right down to the middle. It actually is kind of where it's changing directions. It's coming down, 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 down. Then it stops and it starts going up. This is called the vertex. Okay, then we have this weird stuff over here, the maximum, minimum. This will depend on the value that we pick for k, and we'll see that when we get to the other website. The maximum is whenever k is less than 0. 0. Erase that here. So in other words, if we put a negative number in here, that's going to give us a whole different shape of this, and we'll actually get a maximum value. This will become more apparent later. A minimum value is kind of what we have now. This U shape here, you have a minimum value where it doesn't get any lower than this point right here. And that minimum is caused by having a k value that's greater than 0. Another way of saying this is that if you say less than 0, that just means you have a negative number in there. Or if you have a greater than 0 one, that means it's positive. That's all. So now we're actually going to go to the other website. And the other website that you should go to as well is written down below here on the slide. So make sure you go here. You're going to type this into your Google Chrome. It's www.mathopenref.com and then / quadraticexplorer.html. So take a moment and type that in. I already have it open right here. When you get there, you have to set these ones here to 0. It's B and C. If you just click on this 0 right here, it turns them to 0. I already had it, but if it's on a different number or whatever, it usually starts at something different. Just hit 0 on both of those, and they snap to 0. The only thing we're going to be changing is the number in front of, let's see if I can show you. If you see the number in front of the x squared here, we're just changing that. That's our k value. The rest of the stuff you can kind of ignore. So hopefully that works for you. You can see that U shape. Then we're just going to answer the questions that go along with it. So example 3 part A. What happens to the graph if k changes from positive to negative? So we already have it at a positive number. If you look at it, it's already at 1.2. That's what it looks like at 1.2 x squared. If we change the k value to a negative number, I'm just going to take the slider and go down to negative and see what happens. We have this U shape. Let's look what happens. Now it's negative. Now I'm at negative 1.5. So what happened? I went from 1.2 or 1.3 here to 1.5, negative 1.5. What happens if we go from positive to negative? We could kind of say like flipped upside down. Whatever you want to say there is fine. I could say it turns upside down. This is what I was talking about before. When we change this to a negative k value, now we have a maximum point. It reaches a very tippy top, like a top of a mountain. It's a maximum. Whenever it's positive, we have a minimum point. It doesn't dip below a certain value. And you can see the vertex here is staying right at the origin, no matter what value we have there. All right, how about when k is greater than 0? So we're going to start with a positive k value. Let's start with that. Start with positive. So I'm going to start with 1.5. That's fine. And then what are we going to do to that? And then we're going to increase the k value. How does this graph change? So let's increase the k value. So I'm going to increase it from 1.5. Let's go to like 4 or 5 or so, and just watch what happens. There's 2. There's 3. Here's 4. Here's 5. What is happening to this graph? I'm all the way up to 7. So remember, I started with a positive number, like 1.5, and I went up. What's happening? That's what we'll record. So we could probably say, you can notice it's kind of maybe getting skinnier. It's getting closer to the y-axis. Any of those things would be fine. I'll say it gets skinnier. You know, it starts out kind of wider, but then it kind of gets flattened out. It's not as much of a U shape even when you get that high. We can even go all the way up to 10 where it gets really, really tiny there. So as we get closer to that 1.5, it becomes more of a U shape. All right, and the last one here, when k is less than 0, so we're going to go to a negative number. So I'll start back at the negative, what was that? Negative, let's just do -1. Let's start with that. And then k decreases in value. So we're going to go down. So we're going to start at -1, and then we're going to go decrease. We're going to go down to like -3, -4, -5. How does that change the graph? What do you think is going to happen if we go down to -2, 3, and 4, so on? Well, we'll see. There's -2. Here's -3. And you can see it progressively getting closer and closer to the y-axis, but now the negative side. Again, it's also getting skinnier and skinnier. You can kind of play with the numbers a little bit, and you can see what happens. So it gets skinnier. I would say towards negative y-axis. This is towards a positive y-axis. So in either case, it gets skinnier. It just, depends on what axis is going towards. It's both the y-axis, but here's the positive values, and here's the negative values. Also, let's look what happens if, I don't think I talk about this one here. If we were to go down to, say, 1 or whatever it was, 1.1 here, if we go closer to 0, notice how it's like getting even wider, and it gets really, really wide. So when you get decimals like this is 0.5, this is 1/2, 1/2. When you see a fraction like that, it's really, really wide. It's getting, this line is actually getting closer and closer to being flat. See how flat it looks like here? 0.1. That's 1/10. And obviously, if you put in the number 0, what happens? It goes down to 0. I can't know if I can get to it or not. If I actually snap to integers, it should work. So there's 0. Here's 1, 2, so on, and you go down to 0, and then the negatives start doing the same thing. So as you can see, even small negatives, like -0.2, right, that'd be like 1/5. That's very, very wide. It only gets skinny when you have these big negative numbers or the big positive numbers. So you can play with that a little bit to see how it works if you forget, and to answer some of these other questions here, especially on the homework. Our example 4. In 10 to 12, the bool graph is represented by the equation y equals x squared. So if you notice, the number here would be a 1, because there's no k value in front of there, so you could actually write 1. Give a possible equation for each of the other graphs. So if we look at the bold one here, we're going to be comparing it to the dotted lines there and see what happens. Let's start with 10. Well, if this is just x squared and it gets skinnier, what's going to happen? So let me go to just 1x squared. Okay, that's pretty close, 1.2. And then if we wanted it to be skinnier, well, what number would we pick? Just something bigger than 1, because it's still facing up, right? It's still a U shape. So if I want to do that, I want it to be skinny. If I want it to be really skinny, maybe I would say it's like 7. Right? That's fairly skinnier than what it has there. It's pretty close to the y-axis. I mean, you could even go skinnier. As long as you pick something that makes it skinnier, closer to the positive y-axis, that'd be fine. So I could even just say it's y equals 9x squared. Anything will be valid as long as it makes it skinnier than the one that's there. So it's all valid. All right, let's go down to 11. So 11 is, I think 11 looks like it's wider than the original. It's just on the opposite end. So for it to be wider, right, it has to be a small number, like a decimal, and it's got to be negative because it's facing down. So if the original one was 1, right around here, there's 1x squared, then we want that to be wider, but on the negative side. So we could just make it something like this. How about that? That's pretty wide, right? Maybe not as wide as that. Maybe go down a little bit. There we go. That's wide. That's not as wide there. So that'd be like -0.6. And that would be a valid answer. -0.6. You have to know that it's negative, because it's facing down, and that it's also a little wider, so it can't be as high as the number 1. So I'm just replacing the k values here. And the last one, if we look at that one, it's skinnier than 11, so we have to make sure we go up a little bit in number here. We're going to decrease it from negative 0.6 to something else. And it looks to be almost the same as the bold one that's up here. Would you not agree that it's pretty much the same wideness? It's just on the opposite side. It's just now facing down. So maybe you won't have to do it at all. Maybe this is just the same thing as negative 1. So that way, if we could pop down to negative 1, it's the same thing. Which I think that might be the case, comparing the two numbers here. So I think if it's the same thing as the bold one, it would just be the same thing as 1x squared, but it would be negative 1x squared. If you don't agree and you think it's actually smaller or maybe a little bit wider, then you could say something like negative 1.2 or something like along those lines. But it has to be a smaller number than negative 0.6, like negative 0.8 or negative 0.9. All right, the last piece here, we're going to talk about domain and range. So this is going to be a little different. We have our positive, k values here to make our U shape, and then we have the upside down one. Also the what did I think of? The quadrants are listed here around 1, 2, 3, 4. If you look at those, some of these questions I think in the homework will ask like about the quadrants and where they are. So just know that the first one, the quadrants are in 1 and 2. This is how they're labeled: 1, 2, 3, 4. And then whenever you have negative numbers, they're only in 3 and 4. That's where the graph appears. So they're only ever in 2 quadrants at a time. So domain and range for this is kind of difficult, just because it goes on forever. But we'll try our best to talk about it. The domain is all the x values. So one thing that might be kind of hard to realize is that this goes on forever in this direction, and it does keep getting wider. So it's going out forever this direction, out forever this direction. It's getting wider and wider both ways. And so what's going to happen is that it never stops getting wider. So it actually goes across the entire x-axis as you extend in both sides. So the way we write this is one of two ways. You can use parentheses, not brackets. It never ends in either direction. Parenthesis, you could say it's negative infinity to positive infinity, or there's a symbol that means all real numbers. It looks like an R. You just draw an R and then with an extra line on it. That means all real numbers. That means really anything you can think of as far as the x values are concerned, it would fall in line for the domain. Range is a little different. Range is talking about the y values, and as you can see, the graph never dips below 0. So that's actually a starting point. It starts at 0, and then it goes up and increases forever. So we'd say it's from 0 to infinity. Anytime you use the infinite symbol, you have to use parentheses. If you use a bracket, that means you're saying it closes off at some point, but it does not close off. It's just, we don't know an ending point for infinity, so it just stays like that with parentheses. All right, and then the other one, kind of the same idea. This is growing out forever in both directions. It's going to take care of the entire x-axis. So the domain has the same answer. It's negative infinity to positive infinity, or all real numbers. The range is also very similar, except for now we're starting at 0, going to negative infinity. So if you're going to write that out, the negative infinity has to come first, and then it goes all the way up through to 0. And we put a bracket on 0 because it actually does come up and touch the number 0 there. If I can actually write on it. There we go. So that is the domain and range. For the huddle, hopefully you should be okay with the rest of it. Just try your best, and you can use the website to answer some of the questions as well. I think I might do one with you. So maybe I'll do like number 4 or 5. If the graph has points in the second quadrant, are the values of k positive or negative? So if you look at the second quadrant, let's go back to this. Here's the second quadrant. The graph only has points in the second quadrant if it's a positive graph. So sometimes you have to go back and look at those pictures to see. So the values of k positive or negative, so it would be positive. That's the only time it actually is in the second quadrant. You're given two parabolas, y equals 2x squared and y equals 8x squared. Explain which parabola is more narrow when graphed and why. So hopefully you can just do that on the website as well. So y equals 2x squared would be something like this, just doing a basic thing. And what happens when we go to 8x squared? Well, if we're increasing that to all the way up to 8, it's probably more like this. So which one's more narrow and why? So y equals 8x squared is more narrow. So hopefully you can see why it would be more narrow. It's increasing way faster because that 8 is being multiplied by x squared, so the 8 makes a pretty big difference. So the 8 just makes it rise a lot faster. And you can write that in there as well. I think the rest of the huddle is okay for you to finish. And you can just use the websites to graph them. So that is all for 1 or 2.5.